Below are 4 long straight wires, each carrying a current of 1 amp. The wires are oriented perpendicular to the plane of the paper, and they form a square of 4-meter sides. We want to find the magnitude and direction of the magnetic field at the center of the square. So for the setup on the left, we want to use the right-hand corkscrew rule to tell us the magnetic field direction around these wires. So pointing our thumb into the page, we would see that this magnetic field will circulate clockwise around that wire. We'll have a magnetic field circulating clockwise around this wire. And all the magnetic field lines are going to be oriented clockwise. We'd like to see what's happening at point A. Well, so if this is I1, I2, I3, and I4, the field created at point A by wire 1 is going to point in this direction. The field due to wire 2 will point up and to the left. The field due to wire 3 points down and to the right, and then the field due to wire 4 points up and to the left. Now we can label each of these. This would be what we'd call B1, the field due to wire 1. This one is B2, the field due to wire 2. This guy will be B3, the field due to wire 3. And finally, B4 is the field due to wire 4. We can see here that the total field is going to cancel. It's B1 plus B2 plus B3 plus B4. And that's 0. Now let's try the same idea on this setup. This can be I1, I2, I3, and I4. Let's draw a magnetic field vector for the field due to wire 1. Notice that wire 1, its current points out of the page. So what that means is we're going to have counterclockwise loops. This will cause a magnetic field vector at point A which points up and to the right. I'll call that B1. All right, for I2, we'll just have the same thing. And it looks like we're going to have a field that's directed down and to the right. That'll be B2. Okay, for I3, it's going to create a vector which also points down and to the right. We'll call that B3. And finally, We'll have one more vector. It's going to point up and to the right. This will be B4. We've drawn all the magnetic field contributions from the 4 different wires. Now our job is to evaluate them and combine them through superposition. So I'm going to use the magnitude formula, which was mu naught I over 2 pi d. And I'm going to apply that to wire 1 first. But in order to add these field vectors together, I need to consider the vector nature of this problem. So one option we have is to use a unit vector. And that unit vector can be cosine of an angle I hat plus sine of an angle j hat. This will take care of the directional nature of the arrow. The formula on the left takes care of the length of it, the magnitude of it, and the part on the right takes care of the direction. So what angle is B1 really pointing at? Well, we said that the distance from one wire to the next was going to be 4 meters. That was given above. So this is a perfect square. And if that's the case, then the angle it's pointing at is going to be 45 degrees. And that's what I would use here. That will completely take care of the first wire. Notice that we're going to have another field contribution though, which is going to be equal in magnitude. All the wires carry the same current, so I can add in the contribution from wire 4, and I'll actually use the same angle. Okay. Next, I'll add in the contribution from wire 2. And the angle is pointing toward the 4th quadrant. That's going to be 315 degrees. And finally, we'll do our 3rd wire. And that's the setup. So one interesting thing that will happen here is the vertical components are going to totally cancel out. So we don't even have to worry about these. We can also see that the distances from the wires are all going to be the same. And the currents are all going to be the same as well. So what we're going to really end up with here is going to be 4 mu I over 2 pi d cosine of 45 and cosine of 315 are the same. It's going to be radical 2 over 2. And that'll be a little bit simpler to deal with here. Now when it comes to the distance to the wires, we're going to actually want the distance formula or Pythagorean theorem to find that. Here's our point A, and we want this distance here. It was given that the sides were 4 meters. So if we make a little triangle here, it looks like D is going to be 2 radical 2 meters, according to Pythagorean theorem. So we'll have 4 times 4 pi e minus 7 times a current of 1 amp divide by 2 pi times 2 radical 2 times radical 2 over 2. That's all in the I hat direction. I get 2 times 10 minus 7 Teslas in the positive I direction.